capacitor, and two resistors. We have an electric circuit that contains a battery with EMF of 5,000 volts and a negligible internal resistance, a capacitor of 7 microfarads, and two resistors, 6 times 10 to the 5th ohm and 15 times 10 to the 5th ohm. Initially, switch S is open and the capacitor is uncharged. Calculate the current through resistor R1 immediately after switch S is closed, then sketch the relationship between the voltage V across the capacitor and time t. Calculate the current through R1 when equilibrium is reached. Calculate the maximum charge on the capacitor, then the maximum energy on the capacitor. Then the switch is opened. Sketch the current through resistor R2 as a function of time t. Label any intercepts. Calculate the current through resistor R1 immediately after the switch S is closed. Right after the switch is closed, the capacitor has zero resistance to current flow. So the current coming to this junction here will see zero resistance at the capacitor, and all the current will flow like that. So the current will equal the EMF only divided by R1, and we get 8.3 times 10 to the minus 3 amps. Sketch the relationship between the voltage V across the capacitor and time t. The word here is sketch, so we do not have to put in any max values or minimum values or asymptote values. We just have to give a sketch. So you have a properly labeled graph, volts versus time, and we're charging the capacitor up. And we know that equation, this is something you should really know, is Vmax times 1 minus e to the minus t over Rc. And that gives you a shape just like this, where you max out at Vmax and you start at 0, and it's got kind of like an exponential curve there. Now the trick is the Vmax will not be the battery. Okay, it'll be whatever the voltage is here, but we'll come to that as we continue working the problem. But this is a perfectly good sketch for this answer. Calculate the current through resistor R1 when equilibrium is reached. When equilibrium is reached, that means there is no more current through the capacitor is fully charged. So all the current flows like this. So to find that current, it's going to be the EMF over the equivalent resistance of the two resistors in series. You just add them together and you get 2.4 times 10 to the minus 3 amps. Calculate the maximum charge on the capacitor. Well, we're going to use this equation right here, and we need the voltage across the capacitor. But the voltage drop here does not equal the voltage supplied by the battery. And your maximum charge, which is what we're looking for, is when the system is at equilibrium. So we will use the current found in part C to find the voltage drop across this resistor here, because these two guys are in parallel, so their voltage drops will be the same. So the voltage across R2 is equal to IR2 times resistance 2. So that's 2.4 times 10 to the minus 3 amps, which we got on the previous slide. Multiply that by the resistance, and we have a voltage drop of 3,600 volts. That's the voltage drop we now use to calculate the maximum charge on the capacitor down here. So Qmax is CV on the capacitor, which is the voltage drop across the resistor, R2. You put in the values, and you get a Qmax of 2.5 times 10 to the minus 2 coulombs. Calculate the maximum energy stored in the capacitor. We have our equation here, 1/2 Qmax times the voltage across the capacitor, and your maximum stored energy will also occur at equilibrium. So we will use our Qmax that we calculated, multiply that by the voltage, divide by 2, and we get 45 joules.